Hello and welcome to the bare metal programming series where we are building firmware for a cortex-m STM32 microcontroller. Today we're actually doing something a little bit off the beaten track for this series, which is we're going to be kind of diving deep into the theoretical parts of one specific aspect of this build. And we're not really going to be talking too much about the build itself. So this video can actually operate, or at least I hope it can, as a standalone video just for learning about this topic. So it will relate directly, there will be some details that relate directly to our bootloader firmware update application, and we'll go into all of that. But a lot of this material is just going to go into understanding how AES works. So without further ado, let's get into it. Let's just take a look at these details. So this is what we're going to cover today. First of all, I'm just going to go through some disclaimers. I'm going to throw some disclaimers at you because I think it's quite important to understand the complexities and the things that can go wrong, and just like taking someone's word on a topic like cryptography, right? You really need to be careful with cryptography. It's really something that you shouldn't just do without putting a lot of thought into it. So I will cover some of that. Then we're going to cover what is AES, kind of like what is it the high level, what are the core ideas, like what is it really achieving and how does it do it? And then we'll just move a little bit into this clarification and kind of divergence into what it means to sign something. So all of this, what we're doing here is to get to the idea of a signed firmware update, which is we have authenticated firmware. And so we're going to be just talking briefly about what it means to sign something cryptographically, because actually there are like, let's say, 3 possibilities for the depth in which you can go with this idea, and we're going to see where we'll fall onto that, at least with this very first cryptographic implementation that we go with, and we may go all the way to the end in later videos. Okay, then we're going to cover the algorithm in some detail. I really want to put across a visual picture of how this algorithm works, because you can get away with a lot in just understanding the visuals of this. But we will be talking about some math, and that's something I've been promising for a while. So we're going to be sort of then diverging for a moment into finite fields. And finite fields, they also relate to CRCs, which is something I've been promising that I will explain a little bit deeper. I'm not going to talk specifically about CRCs, but we are going to talk about some of the mathematics that goes into both AES and CRCs, and I think you'll have a much stronger grounding to go and learn sort of the real details about each if you know a little bit about finite fields. So once we know a little bit about finite fields, we can kind of bring that back into the last parts of AES. And then we're going to talk about the modes of operation, which are the different ways that you can actually apply this algorithm, right? The algorithm is one thing, and then how you apply it over various forms of data, that's a kind of completely different and also complicated subject on its own. And finally, we're going to finish up with the specifics on we're actually going to talk about a couple of different modes of operation, but we're going to talk specifically about CBC MAC, which is the mode of operation we're going to apply for how we authenticate our firmware. So CBC MAC is the final version of this that we implement. All right, so all of that, let's get to the disclaimers. Let's get those out the way. Now, I do actually want to exercise some humility here, right? I am not an expert. I'm not a cryptographer. I'm not a mathematician. I'm a software engineer. So understand that I am not a sort of the highest level source of truth that you can get on this, right? I know that I don't know enough about this subject area, but what I know is that I've learned enough about this to see all of the complexities and to know that there are many, many ways that this can go wrong. And what I don't want to do is to paint a picture to you that it's actually quite simple, right? If you just get this idea, it's really simple, because that's not the case. It is really, really complicated, right? People are very, very actively, getting PhDs and postdoc stuff all over the place in this subject area. Right? It's not slowing down. Like, this is a complicated area. But yeah, it's not that you shouldn't learn about it. You should learn about it 100%. But understand that I'm not the expert, so don't take my word as the be all end all. And please don't point it out to me, right? You should point it out to me, but don't, hold me to the highest standard if I happen to misrepresent some aspect of a complex idea. I will try my best not to do it. All right. All of this whole series is meant as an educational demonstration, right? I also mentioned this way back in the very first video in this series, right? Everything that we're going to be doing is meant as kind of educational. Don't take it as I can take this code and throw it into production. It's not really meant that way. This is really about kind of painting the broad strokes of a lot of different things and a lot of complex and interesting ideas. And if you really want to do them justice, you need to go a little bit deeper into everything. So just with anything in this series, the actual cryptographic stuff that we look at is only going to go to some amount of depth, right? We're not going to be able to get all the way to the core. So don't think that you can take this and throw it into production. Don't do that. Don't do that with any of the cryptographic code that we look at. Okay, so if you do happen to write your own cryptographic system, that's fine. It's good. Go deep, learn about it. But if you're going to put it into production, especially if you're going to put it, you're selling devices, you work for a company, you need to do the due diligence of actually having it independently vetted by a third-party company. I don't have any. I'm not recommending a company here. This isn't a sales pitch, but there are just ways to get this wrong that you couldn't even imagine. Right? They feel like magic. The ways in which this can go wrong. Someone can just monitor the power signal. Someone can monitor the power consumption of your device and extract a key from that. Right? If you don't do this in a certain way, it's really easy for someone to extract your secret key that way. So yeah, you knowing that stuff, not even the mechanics of the algorithms, but knowing that if you don't implement that specific algorithm in a certain way, that you can just leak the information out, right? Have another company look at it, because they're meant for this kind of stuff, and they can say, hey, this part, if you improve that, then it's golden. All right. Some parts of this demonstration I will leave intentionally insecure. And that is because I might want to explore how we exploit weaknesses in the future, right? I might actually want to look at some of that stuff that I was alluding to just now. So some parts, I know that it's not the right way to do it, especially in production. This isn't a production system, but I'm leaving it in there intentionally. So keep that in mind. But do point it out to me if you see anything wrong. Finally, of course, I or someone else, probably not me because I'm not an expert, but someone could dedicate an entire series to this. And of course people do, right? They're called courses and you can go and take them to universities and stuff. But if any of this piques your interest, this, all of the material, that's the coolest thing about cryptography. Almost all of it's done out in the public sphere, right? Cryptography is not something you try to keep secret because that makes it more insecure. So if something's interesting, go down the rabbit hole, read the specs for AES, read the original entry for the NIST application for AES, all of those things. Some of those documents, which I'll link in the description, they actually cover not only the mechanics, but all the justification and the mathematical reasoning and the idea of the trade-offs they're making in order to make one decision or another. All of those details are actually not going to be covered today because we just don't have the time, but they are covered in the documentation, and it's great. It's hard to follow some of it, but if you just want to understand, yeah, okay, I see that it works this way, but why? That's where you'll find it. Also, by the way, if you like reading documents, I actually wrote a blog post, which a lot of the information and the kind of visual resources I'm going to be using today from this. I wrote this document last year, this blog entry called Rolling Your Own Crypto, Everything You Need to Know to Build AES from Scratch, and then never use it for anything of consequence. I wrote this, and yeah, if you kind of want to process this in a different way after the video, or you just prefer reading for this kind of material, I'll link to this down below as well. Alright, so now we've kind of disclaimed, let's talk about what AES is. So AES is the Advanced Encryption Standard, and sometimes also known as kind of this wider family of similar algorithms called Rijndael. I think I'm doing that name the best justice I could. I know that if you read it online, some of those pronunciations are nowhere near where it should be. But okay, so it's a widely used, probably the most widely used, symmetric block cipher. So basically, the symmetric part here refers to the fact that we use the same key for encryption and decryption, right? You also have public key cryptography, where you have two keys, right? One is a private key and one is a public key, and you encrypt with the private key or the public key in some cases, and you can decrypt with the other key. But you don't actually, no information about the keys is revealed by doing either of those. So some systems use that, and many systems use that in the modern world. But AES uses a symmetric key system. It's still secure as long as you don't, leak your keys. But it's extremely secure. AES is probably one of the most secure, actively used algorithms out there. And it's a block cipher. And what a block cipher means, and this is kind of probably the more important point, is that plain text data is grouped up into blocks, right? So you don't just take one byte and encrypt that one byte. You actually take a series of bytes, 16 bytes in the case of today. Take 16 bytes and you group them up into a block. And all of what we're going to call the encryption, it all happens on that block. It's on the block level. So if the implication there, of course, is that if you don't have enough data, if you don't have a full 16 bytes to encrypt, you actually somehow need to pad that out. You need to create a full block. You can't encrypt less than one block. So what does a block look like? It kind of looks like this. This, you can imagine, is your input data stream, and it goes on and on. There's a whole bunch more data. What we actually do to create a block from this is we just arrange all of these values into a column-wise, 4x4, in this implementation of AES. And you come out with this. So on the leftmost column, we've got the first 4 values. On the next column, we've got the next 4, and so on. So this is our data structure, if you will, right? And you can represent the data structure any way you want. Obviously, it makes sense that you could just have a continuous array like this, which you work out the right indexes to, or you could use a multi-dimensional array. There are many different things, different ways you could do this. You could also, if you're looking at this more abstractly, this is also kind of like a matrix as it is now, and you can think about it as being a matrix, and many of these operations can be done in using those kind of operations, matrix operations. Okay, so we've got 16 bytes, that's 128 bits, and that's where the name of this particular version of AES that we're going to be using comes from. This is AES 128, which basically means that we're operating on 128-bit blocks, and the key size is also 128 bits, so also 16 bytes. All right, so this is it. And the core idea here, the main thing, if you sum it up into one sentence about AES, is that encrypting a block is really just a reversible combination of shifting, mixing, substituting, and otherwise shuffling data around in a block with some data derived from your secret key. So you're just doing a bunch of relatively simple operations that are all reversible in some way. And that's how you can get back, right? That's how you can decrypt. If you've got the key, then you can just reverse all the operations you did, and you get back to that original block, and then of course you unpack the block, and eventually you get your actual data stream. So that's kind of the core idea. That's how this stuff works. And the various ideas of the shifting and the mixing and the substituting, all of these things which are, different ways of operating on the columns and the rows and the individual bytes of the block, all of those things, they have different mathematical properties that lend themselves to making this very hard to go, in the reverse direction, right? Without the secret key, it's essentially impossible to get back to the original data, at least with today's technology. So yeah, and probably for a long time in the future as well. Okay, so let's just take a little moment to think about what it actually means to sign something. So in essence, what it means is that we can send a message in plain text, right? In our case, that's sending a firmware update. We've got a whole bunch of bytes, that's our firmware. And we want to say, like, are we the ones that actually sent this, right? Did we authorize this firmware, or is it some random firmware that the guy down the street made? That's one of the things that the signature process, or signing the firmware, actually does for us, right? It allows us to verify the authenticity of the sender. So that's also why we use it in communications, right? Because you want to make sure that the message you got was from the person who said they sent it. It's not some man in the middle attack. It also has the benefit of being able to verify the integrity of the message, right? We can say that the message that I got and the kind of the signature that goes along with it, when I actually check that signature against the message, if they don't match, it basically either means that the authenticity wasn't correct, or that the message got corrupted along the way, or the signature got corrupted, right? So it's telling us a bunch of information like that. But if we know it checks out, if we can validate the authenticity or verify the authenticity, then we can say that the message is also complete and intact and has the integrity. So we can think of this signature being a little tag, right? Something that we're going to send along with the message itself. That means that, well, in our case, in the firmware update, we've already looked at this, that we kind of took a CRC of the firmware and then we embedded that CRC inside the firmware itself. So that when we do the update, we can just go and find that CRC and compute it over the firmware and actually make sure that, well, everything matches. Now, you can see at the bottom we've got a pedantic hand raise here, and that is because there is actually kind of a spectrum of this, right? From what I just mentioned, going all the way to really, really secure, right? So putting a CRC is not that secure because anyone can compute a CRC. So we kind of end up with this spectrum here. So on the left, we've got our hash. So a hash is just a non-secret function. It's just a function that we know how to do that takes our, variable length data and digests it into a fixed sized value. And the idea with a hash is that it's a one-way function, right? It's a compression of sorts, right? We're taking a lot of data and squishing it down into a smaller amount of data. But the nice thing about it is that it's easy to compute, and therefore we can always do that with, say, a firmware update or a message that we've received. We can sort of check it against its hash, and we can say, hey, actually, it was corrupted or it wasn't corrupted. This is why we put CRCs in everything, from like our packets in this series to the packets that fly around on the internet. Like, this is why we use CRC, for example. But there are many hash functions out there, SHA hashes, SHA-256, that kind of stuff. That's also a kind of hash function. But it doesn't tell you anything about the authenticity of the message, right? It doesn't tell you that I made it or someone else made it. So for that, to move on to that next step of more security, we have to use something called a MAC. A MAC is a message authentication code, and it's another fixed size value, just like hash, and we generate it using a secret key and a symmetric encryption function. So this is what we're going to be doing, right? This is what we're going to do with AES. We're going to take our message and, our message, our firmware. We're going to use our secret key to do some sort of encryption. And in the end, we come away with this other fixed size value, which basically acts as a cryptographic hash. And a MAC can only then be recomputed by someone else who has the same secret key, right? There's no way for you to compute this hash which is good, right? Because that means you can't verify that you're the person that sent it, but you also can't check that I am the person that sent it either. That is why the secret key is going to need to live inside our firmware. So that is going to allow us to run the same process that we use to sign on the PC side as we do in the firmware to check that it's valid. So this can be used to verify both the integrity and the authenticity. And finally, all the way on the most secure side, we have a signature. And this is kind of where, terminology, I'm using terminology like somewhat incorrectly here, right? We're talking about signed firmware. Technically, what we're going to do is not a signature in the cryptographic sense, because a signature is another fixed size value generated using a private key and an asymmetric encryption function. And the difference here is that we can generate this tag, this fixed value, using the private key, but then we can validate that using a public key. So the public key is like known information to everyone. Well, yeah, not necessarily that we give it away to everyone, but it's not a secret in that sense. So the thing here is that we can actually check that the firmware has integrity, that it's authentic. But also the big benefit here is that if someone manages to dump the contents of our flash from the chip, which of course we don't want them to, but it is possible to do that, and there are attacks to be able to get that right, then we're actually not revealing our secret information. You can imagine that if they were then able to get our secret key for AES, anyone could sign any firmware from that point onwards. And if we had the same secret key in millions of devices, suddenly all of those devices are no longer secure, right? If someone posts that secret key on the internet, or they sell it on the black market, or whatever they happen to do, they don't even share it. They just have it, in their criminal organization or whatever. Or their nation state organization. I guess there are multiple things. One of those is more likely, actually. Even if they don't tell you, basically you're screwed, right? Like, at that point, you haven't been able to protect your secrets. Whereas with public key cryptography, you can protect your secrets, even if someone manages to get something that you didn't want them to get, right? As long as they didn't get that private key, they can get the public key, but they can't get the private key. All right, so that is kind of the spectrum here. And what we're going to be doing for today and for the coming episodes in the series is building a Mac, right? We're going for this middle step. And maybe in the future, we'll look at the signature step as well. All right, so let's kind of cover the algorithm, because this is the coolest part of AES. I think that understanding this is well within everyone's range, right? Anyone can understand AES, I believe. With a bit of dedication. There is a little bit of a hill to overcome with some of the mathematics, but if you're willing to put the time in, you can definitely understand this. Now, understanding it is a little bit different from being able to create it, right? Just like I can go into a museum and I can look at a painting and I'm actually not an art person, so I can't easily do this, but let's say anyone can go into a museum, look at a painting, they can connect with it emotionally, right? They can feel something, and maybe they can even feel what the artist intended them to feel on the inside from viewing that artwork. So in that sense, anyone can understand the artwork, but that doesn't mean they can make the artwork, right? That doesn't mean that I could then sit down and paint brushstrokes with oil paints and use all the techniques to create that. Those are two very different skills, right? The understanding and the creation. So this is the big part about don't roll your own crypto. One of them is hard to implement, so you could be insecure there. Definitely don't just try and invent your own crypto. That's the worst thing you could do, because you will definitely get that wrong. Because the complexities of the operation is not the complexity of the underlying idea behind it. All right, so this is the overview of the algorithm. We do something called key expansion. That's where we take our 16-byte secret key and we run it through a process that gives us like a longer secret key, right? we're not going to magically get more secret information out of that, but what we can do is kind of diffuse that information over a larger area and use a larger surface area to transform the data and make it even harder for someone to get back to the original than if we were to just use the small initial key, the 128-bit key. Then there is a step called the addition of the first round key. That's basically where we just mix the secret key, or we get a series of round keys out of this key expansion. So we get, from going from one key, we get like, say, 11 keys that we're going to use. So they're called the round keys, and we add that together in some way with our main input, so that already scrambles it up a little bit. And then we run it through a series of rounds. So for every one of those other keys that we got out of the key expansion, we basically go in a for loop here, and we do a whole bunch of rounds where we do something called substitute bytes, where we literally substitute one byte for another, like it's just swapping according to a table. Then we shift rows. Well, it's actually almost like the name sounds, right? We literally shift the rows around in the block. Then we mix the columns. This is a little bit more tricky than just sort of moving the columns side to side. We actually go through the most complex process here to diffuse the information in each column over like the whole block. And then finally we add the round key for that round. So it's the same thing up here as the first round key. And that first round key is actually just the secret key, the original secret key. So we add the sort of expanded derived key that we got there for the next one into the mix. And we do that a whole bunch of times. So we do that 11 times, I think. 10 times, 11 times. And then we have a final round, which is the same as all the previous rounds that we did, but we don't do the mix column step. Which is kind of interesting, but as it turns out, and you can read about the justifications, the mix column doesn't really make it more secure for that final step. So it's just omitted, right? Because it's computation you don't need to do. All right, so that's the high level overview. Let's look at each of those steps in some detail. So the first one is the substitute bytes step. And I told you, right, it is literally just taking a table of information, right? So here we have 256 bytes in a table, and you basically say like, hey, I've got the byte 74 here in my block. This is my block. My first byte is 74, so I go to my table and I kind of find the 7 here, and I move along until I find the 4, and then that's the byte that I replace that with. I replace it here with hex 92, so that's what we get out on the other side. We do that process for every byte inside the block. And so this table is called an S box, a substitution box. And there are two different S boxes for the encryption step and the decryption step. And, well, they're just inversions of each other, actually. So it's basically like the encryption S box is taking you from one way, and the decryption is taking you the other way around. Now, these tables are not just pulled from thin air. They're actually designed, and they're generated from a mathematical function in GF 2 to the 8. So that's a Galois field, 2 to the 8, specific field here. That probably won't make any sense to you. We are going to get to it, but I'm just going to mention it here. Like, this doesn't come from nowhere. And there is talk, right, of there's been discussion over the years about if you were going to put a kind of backdoor into the algorithm, this is where you would put it. You would put it in this step here, because this S box, the idea of it is to actually remove some of the linearity from the whole mapping that we're doing. So mathematically, what we don't want is that you have, like, this encryption process is what you would call a linear function, because a linear function means that you can do a whole bunch of complicated stuff on the inside, but eventually the stuff that comes out, you could just skip all of that and write a function that takes your inputs and turns it into your output. Like, that's what it means to be like a linear function in some respect. So what this table is doing is removing some linearity from this whole thing. It's a remapping that isn't as simple as just being able to write a linear function. Okay. So the next step is the shift rows step, and this is another case of just like good naming, you know, like we take some of the rows and we shift them to the left. So we take this original block here. The first row we actually don't shift it. The second row we shift by 1, so we sort of shift all the bytes out, and you can see these bytes, they end up getting pushed out of the block, and we sort of just take those and we shift them back. So the whole thing is actually rather a rotation than a shift. So we're sort of rotating bytes around. So here we rotate 2 bytes out, we rotate them back in. Here we rotate 3 bytes in and we rotate them back out to the other side. So this is kind of your resulting block. And if you kind of just look at the colors of how we started and how we ended up, if you're a non-colorblind viewer, if you're a colorblind viewer, of course you can just look at the numbers and you can see how it's mixed up. But here you can see that you end up spreading out. I mean, you still get a pattern out of it, but you spread out this original column-based operation that you have. And a lot of AES is based around columns. So the fact that we can remove some of this like column orientation with this step is what makes it a bit powerful. Okay, so that's the shift row step. Literally just shifting the bytes around on a row basis rather than a column basis. Okay, and then we get to the mix columns. And the mix column is probably the most important step. I mean, they're all important steps. This is a teamwork operation, so to speak. But mix column is basically doing something really important, which is it's diffusing information within the block. And what that kind of means is that this step means that if we change a single bit in our input, like our plain text, that has an impact on multiple bytes on the output. So I flip one bit here, it doesn't just flip one bit on the output, it flips a whole bunch of bits, and it moves things all kind of around in a way that is not easy to get back to. Right? It is reversible, but it's not obvious when mixed in with all of the other steps. So this typically uses matrix multiplication. So this is our block column. We do this on a column by column basis, right? Mixed columns. We take one column in, we do a matrix multiplication, and then we get this on the other side out, right? So, the new block is the result of this operation on one column and this matrix. And again, this matrix is fixed, right? This is another sort of like, magic value in the algorithm, so to speak. This doesn't change. You can change it potentially if you want to make some non-standard version, but again, this is justified in the documentation. So if you go and read the papers that were like describing the original algorithm, you can see how they got to this. And again, this is something that they got to with this Galois field, 2 to the 8. So really, if we're gonna, one more thing about the Galois field is that this matrix multiplication, if you're familiar with matrix multiplication, which you may be if you've done something with graphics, or if you've studied some linear algebra, or if you've done any machine learning stuff, you'll probably be a little bit familiar with the idea of matrix multiplication and the fact that you can have this object, which is a bunch of numbers or mathematical objects inside a matrix, and you can multiply it. And multiplying a matrix means something specific, right? It's not just regular multiplication, matrix multiplication. But this is not even regular matrix multiplication, right? Because this is matrix multiplication using multiplication inside this Galois field, GF2 to the 8. So yeah, it's about time to take a divergence into finite fields or Galois fields, and this is going to be a little bit mathy, right? We're gonna not too much. If you're comfortable with mathematics, this should be all right. But this can be a little bit intimidating. It certainly was for me when I was reading, at least. So maybe for everyone else, it's like a walk in the park. Okay, so what is a field? So that's kind of the first port of call on this whole thing. So a field is a generic description of a kind of mathematical system. So a field is a collection of elements, right? so a set of elements with a valid definition for some kind of addition operation, subtraction, multiplication, and division. But these operations aren't they're not what you know in everyday numbers. They're some more generic version, right? This is mathematics getting really generic. And fields and rings and groups and semi-groups and all that kind of stuff, that's part of this larger field of mathematics called abstract algebra. And it's the idea of kind of understanding that hey, we've got numbers and we can do algebra on them, and we understand that there are a bunch of ways in which these numbers behave when we do these operations on them. And actually abstracting that one level back and making it more generic and understanding that, well, we don't only have to use integers or real numbers or quotient numbers or rational numbers, all of these different numbers that we're familiar with, complex numbers, but we can actually create many different kinds of mathematical objects, right? And they all have various operations that they can do, but they all have to behave in a similar way. They have to adhere to a set of rules in order to be classified as a field or a ring or a group. So in our case, a field is the set of elements that have these operations and that adhere to a fixed set of axioms, so a fixed set of rules that these operations must obey. And if they do that, you can say it's a field. So that's a field in general, and then a finite field is a field where the set of elements that you have is finite, right? There are only a fixed number of elements inside this set, because you can have fields that are infinite, right? You can have a field of of just numbers, right? And numbers are infinite, so you could just go on and on and on with the numbers. So in that sense, that's an infinite set, but a finite field has just a fixed number of elements. And performing an operation on any of the elements in a field always just produces another element of the field, right? You can't escape the field. So if I multiply two numbers in a Galois field, I'm going to get back another number in the Galois field. All right, so that's what a field is, and it is suitably generic, right? This is the land of the generic at this point. So here are the set of rules that objects that are a field, like mathematical objects that form this system, a field system, have to obey. So the first one is associativity. So if I have my addition operation and I've got I'm just standing in variables here for the operations, if I've got A plus B and then I do plus C, that has to be the same as if I did I did B plus C and then A, right? Then plus A. So the order in which I do the addition operation cannot have an effect, right? It cannot be different that I do A plus B plus C versus doing B plus C plus A. So that's the first rule. And we have to do the same with the multiplication. So that also has to obey this same property. So then the second axiom is commutativity. So what that means is that we can do the operation on these two elements, but if we have something on the left hand or the right hand side, that can't have an effect on the operation either. So A plus B has to be the same as B plus A. A multiplied by B has to be the same as B multiplied by A. And that's true in normal numbers as well, but there are of course operations where that's not true. So if you do A divided by B, it's not the same as doing B divided by A, right? So those are operations that don't have this property. And yeah, of course you can build systems that don't obey these axioms, but then it wouldn't be a field. So it's totally legal to do it, but it turns out that if you build systems that don't follow these rules, they're not very interesting. And they don't really map to the real world much either as well. Okay, so identity, that's the next property. Basically what this means is a fancy way of saying that there's some kind of element inside the fields that we'll call 0, right? It's not actually really the number 0, but it's some element that's neutral, that when you use it in an addition operation, like you do A plus this 0 element, you just get back A. So in real world, in numbers, 0 is that element, right? If you do any number plus 0, you get the number back. Same thing with the idea of a kind of a 1, right? It's not actually the value 1, but some 1 such that a multiplied by 1 gives you just back a. Alright, so that's identity. And then we have the idea of an inverse. So an inverse is that, well, for every element a in the field, this is for addition. Some field f tried to be a little bit formal here in building up the language. There exists an element which is negative a or minus a, such that a plus this negative a creates 0. That's what we get out of it. And we know that negative numbers work like that, right? For integers, right? We have negative integers. So if we do 2 plus minus 2, that gives us 0. So inverse for multiplication, it's just the same thing. We have some way of inverting the multiplication such that we must have an a to the negative 1 power, or 1 divided by a, such that if we do a multiplied by this inverse a, then we get back 1, or the 1 element, whatever that 1 element happens to be in our system. And finally, we get this distributivity of multiplication over addition. So what this means is that we can basically do this kind of algebra on it, right? So we can take an expression in this form, a multiplied by b plus c, and we can transform that into a different expression, which is a multiplied by b plus a multiplied by c. So this is basically, we can do algebra on it. We can do normal algebra rules. So if we build a system that happens to have all of these axioms, right? We make a set of elements. We say these are all elements what we have. These are the operations. This is how the operations behave. And look, the operations, they observe all of these rules correctly. Then we have ourselves a field. So the finite field that's used in AES is something called GF2 to the 8. And basically this is kind of this in itself is kind of notation. So on the one side, 2 to the 8 is 256. And that's actually the number of elements in this field, right? And you'll notice that that happens to also be the number of valid values in a byte. So that's quite useful. But what it's also telling us is that this is almost represented as a byte in the field. So we actually have 8 elements within our object, and they can each take on 2 values, right? They can take on kind of a 0 value and a 1 value. So we're getting closer to this idea of binary. And this is why Galois fields in particular are used kind of all over computer science, because there is this very strong, and this is not all Galois fields, right? But this is at least like the ones that are useful in computer science. They map very strongly onto binary numbers, and like that's kind of the bridge that we're building. We can take all of this crazy kind of almost, like for lack of a better word, like magic that we have out there in the world of mathematics and the discoveries and the theorems, and we can project that onto this very concrete real world system that we've built up of kind of building transistors that are able to take on 2 states and doing all of this kind of stuff. So the finite field we use in AES is GF2 to the 8, and as it turns out, we can actually make both our addition and our subtraction operation XOR. That's really cool. So actually, you probably know, if you've done some some low-level kind of building adders out of logic gates, you probably already know that addition is kind of just based around XOR anyway, right? If you do addition on the logic gate level, like the main addition operation, the sum part, happens with XOR. And XOR just is the kind of addition operation within GF2. So you can actually kind of go through the rules and see that it is, like, it obeys all of these axioms, like associativity. If we do A XOR B XOR C, or rather B XOR C XOR A, it's the same as doing it in any other order, right? The order doesn't change. We have commutativity, so if we do A XOR B, it's the same as B XOR A. Sorry, let's go back one. If we do identity, well, we can actually use literally the number 0 here, kind of as our 0 element. So A XOR 0 is just A. That happens actually in XOR as well. And inverse, well, every element is its own inverse. So A XOR A gives us 0. And that's true, that used to be true as kind of the fastest way to set a register to 0 in an assembly language, was to do XOR of that register with itself, because like that was usually a one cycle operation to set something to 0, whereas just moving some value, 0 value into a register was actually used to take longer. It doesn't anymore, but it used to. Okay, so these are the operations, and you can try to convince yourself that this works. It's kind of not the whole story, because of course we have the idea of multiplication, and there things get a little bit more complicated. But before we go into that, like formally speaking, in the mathematics, we don't just have like binary numbers. We actually treat all of the elements of GF2 as a polynomial expression. And a polynomial expression, if you haven't come across that before, is basically something in this form, right? So we've basically got a big addition operation that's happening over a bunch of kind of variables. So these x to the n. So we have an x that's raised to an n power. So we have, like in our case, well, for any number of kind of elements within the set, you can have these items raised to a power. So x to the n minus 1, all the way down to getting down to 1, which would be here, and then kind of the 0, or the however you want to see this. And this follows this pattern, so x to the n minus 1, x to the n minus 2, kind of going down with powers as you go along. And finally, of course, this one doesn't have a power up here, so then the final one here is just a constant. And this constant value here, this a to the n, well, this is the constant associated with each of these elements here, or I shouldn't call them elements. Elements are the whole thing in the set. I told you that I would mix my terminology and everything up with this. I'm not a mathematician. All right, so this constant is multiplied by the polynomial value. So each little part that makes up the polynomial expression has its own constant. That constant can be 1, it can be 0, it can be 5, whatever you want in general. We can have a constant associated with this that's multiplying. And then the final value is just a constant or not, right? That's the thing. And these map on to bits, right? So like in the case of GF2 to the 8, these map directly onto bits in a binary number. So like this polynomial expression here represents this, or is equivalent to this binary number. So how to kind of read this out is that we have an x to the 7 here, and this is kind of representing this bit 7 over here, from a bit 0, 1, 2, 3, 4, etc. up to 7. So this represents that we have a 1 bit here, and then we get x to the 3. So what that's telling us is, well, the next 1 bit is the bit in position bit 3. The 2 is then here, and then finally we have this constant 1 on the end that represents the very last, least significant bit. And of course, if you go back, remember we just have a constant here on the end, so that's what that 1 is doing for us. And something to note here is, of course, we don't have these constants alongside every element here, except for the end, of course. And that is because the coefficients are always either 0 or 1 in this Galois field. So, well, by default, right? If you the only things that really make sense are having a coefficient of 1 or having a coefficient of 0. So we just don't write them here, right? If we have this x to the 7, this just means 1 times x to the 7. We don't need to specify that. And likewise, we don't need to say 0 times x to the 6, because we can just instead omit it, and then the 0 in that position is implied. So this is kind of how to read these expressions and how to turn them into binary numbers in your mind. So that's that. That's kind of, I hope you're with me up until this point. It is abstract. We will get to getting more and more concrete. But now we can start to talk about multiplication. And this is where it does get tricky, but also is not that complicated if you've done some algebra in your time. So let's take an idea like hex 42 multiplied by hex AB. Let's say we wanted that expression. Well, that's equivalent to kind of breaking out to these binary bits, and then we would have these two binary expressions multiplied together. So now we can turn these into their polynomial form, right? So we're just going to go the other way. We're going to take something in this style and we're going to represent it as a polynomial expression. So yeah, so in this case, right, we've got a bit set in the 6 position. We have a bit set in the 1 position. This is 0. So what we have is x to the 6 plus x. So that one is just, it doesn't have the 1 up top here, it's just x. Okay, and then we take this one, which has all of these bits set, and that translates to this expression. So what we're saying is that we want to multiply these two polynomial expressions together. And the cool thing about the way that this just works is, well, one, we need to adhere to the idea of using our axioms and the fact that we've set our addition operation to work in a certain way. But the rest of this, we can just use algebra, right? So we can just use the rules of algebra to sort of simplify these expressions. So if we take this, we can actually simplify it using like just regular old foiling out kind of approach. So we sort of just like take each element and we multiply it together with the element in the thing that we're trying to do. So we do, for each element here, we're going to try and multiply out and expand our expression this way. And the cool thing is that with these polynomial expressions is that the way this works, right, is that you just add the powers. So that's how this multiplication works in terms of just multiplying things with powers in algebra, right? We just add the powers together. So when we multiply x to the 6 by x to the 7, we get x to the 13. And when we do the same with x to the 6 with x to the 5, we get x to the 11. And then we're just adding these expressions together, right? So we do that here for x to the 6 for all of these, and then for the x over here, we do it for all of the other elements. So then we get this expression. And of course, this is just one big long addition expression. So we've got all of these, and you can see we've got some repeated elements here. So like x to the 6, we've got an x to the 6 here. Well, that would give us 2x to the 6 if we kind of added those together. And because of the way that this works, right, values are only ever 0 or 1, and addition is XOR, right? So when we XOR two values together, which are the same, that gives us 0, right? We know that from these from this like axioms that we did. If we XOR something with itself, it gives us this 0 element. So, like knowing that, we can take these two x to the 6's, they just cancel each other out. So they get removed from the expression. So when we kind of simplify the whole thing down as far as we can, we get this. So x to the 13 plus x11, 9, 8, 7, 4, 2, and then finally this x on the end here. And when you translate that back to a binary number, it comes out to this quite long number, which is larger than 8 bits. And as we said, there are only 256 elements inside this field. And when you do any kind of operation, multiplication, addition, subtraction, division, you have to get back an element that's also inside the field. So this is not the final result. We need to take this result and do one like kind of final step on it in order to get the final answer. And that step is using an irreducible polynomial. So what we're going to do is we're going to take this like expression that's going to fall outside of the field, and we're going to reduce it with this special polynomial. And the way in which we do that is we use the modulo operation. So we're going to basically extract the remainder after we divide this long number by this one. So when we take our polynomial and we convert it into the binary form, that's basically what we're doing. We're doing this modulo expression here. And when we do that, when we actually kind of run that operation through, remember division is really just subtraction, and subtraction is just XOR, right? XOR is the same for addition and subtraction. So this makes it really easy. If we want to do like a division operation, we're just XORing numbers together again. So we can actually use that to do some long division, basically, some classic long division, and that will give us this answer. And eventually what it gives us is this, which turns out to be hex 46. So the result in Galois field 2 to the 8 of doing hex 42 times hex AB is that we get hex 46 back. That's probably not your expected answer, and that might not be a very useful answer in the real world, right? If we want to do some mathematics on the numbers, that might not be a very useful result for us, right? If we want to do something like numeric with it. But it's going to be really, really useful for us in this case, because that is an unusual answer. It's not an easy function, right? That is not you cannot just model that function that we've just done to get to this point linearly. So the fact is, when we do these operations, these multiplications, we get this non-linear result, but it is invertible, right? We can sort of go back the other way and get back to our old answer, right? So that is why this is so important. And just let's take a look at the kind of the long division step here. This is long division using XOR as our subtraction, and you just run it through just like you would have done at school, right? And you've probably also forgotten how to do this because no one does long division anymore. But basically there are just some rules about how you go through it. You can always just like look up how does long division work, go through it, kind of you just go like bit by bit on these items and you work out and you sort of shift things down until you get to the final result at the end. And that's it. That's how this thing works. Of course, when you implement this in code, you can use different algorithms in order to speed this up and do it differently, but fundamentally this is the operation. Like, this is what we're doing here. So we've taken this idea of a abstract mathematical idea, right? There are these things called Galois fields where they behave in a certain way, they have these particular axioms, we can construct them having these set of elements behaving in a certain way. We can use that as a tool to process our input in an interesting and difficult to reverse engineer way. Okay, so CRCs are also based on Galois fields as well, right? All of this, when you take a CRC, you're also kind of converting your numbers to polynomials and operating inside the Galois field where you use XOR as your operation. You have irreducible polynomials there too, and kind of the details of the actual algorithm CRC are different to what we're going to be using the Galois fields for in this case, but it is the same underlying system. So, you know, this is not going to be enough for you to like feel like, yes, I've cracked this thing, but you can start like implementing code to do this whole process we've just seen, and you can test it against the set of test vectors that they have in the AES specification. So all the AES documents actually contain basically test cases, which you can put in your code, and you can run the stuff, and you can see if you get the right answer on the other side. And you can kind of tweak all your parameters to get this right. So you could probably try already to go and implement this in code. And I strongly advise you do that. It's not cheating to go and look at more resources or read Wikipedia. Definitely do that. Read other people's code as well. It's actually not cheating. I don't know if other people had that conception when they were learning to code, but I always thought that it was cheating to read other people's code. It's not. It's really not. It's just like, that's the trick. That's how you do it. All right. So now, if we kind of go back to this mixed column step, we can now understand that matrix multiplication is just, right? Of course, because it's not simple, but now we understand kind of all the little bits and pieces, or at least we can put a name to them. We can say, well, it needs to go through these steps. We don't need to understand it, but we can understand that it's just a series of GF2 to the 8 multiplications using the values in the columns by the values in the matrix, right? So we're going to apply regular matrix multiplication rules, but the multiplications that we do within that, we're going to use Galois field multiplication using the Galois field we've defined with XOR and all of that, and that's how we get like the output of this mixed columns operation. And I hope now if you kind of just like reflect this back through, you can kind of get a sense of how this is actually then like diffusing this information out, because like we're totally not getting the, like if we add or multiply two numbers together, we're totally not getting the result we would expect, but we are like somehow then spreading this information all throughout this throughout the resulting vector using this matrix. So we're spreading that information out in a way that we can reverse it, but it's totally nonlinear, and yeah, it's really cool. Right, and then like finally, this is actually the first step of the algorithm, but I think it's worth it to talk about it at the end, because now we have the context of all of these operations. Now we can talk about how we take our secret key and we expand it out into these round keys that we're going to use to basically do a whole bunch of these operations again and again and again using different round keys each time. So this is also known as the key schedule. And again, AES has different like key lengths, so you can do it with 128, 196, and 256 bit keys. We're talking about 128 here. We're going to take our first initial secret key and expand it out. And the process is just another series of transformations, very much like what we've already looked at. But we do all of them on a column basis here. So what we actually do is, this is our original secret key. This is basically a block here. You can imagine this is the block, and we've kind of pulled it apart into its constituent columns. And this is the first round key. So this is still just what we use. This is the initial round key. But to compute the second round key, well, what we do is we take this final column and we plug it into something called rot word, which is rotate word. And that is an operation that we'll look at that basically shifts the bytes around. Then we take the result of that operation and we plug it into something called subword, substitute word. And that is very similar to when we did substitute bytes earlier on, right? We're substituting using an S box. We're using that big table of things to substitute a value. And then we do something called archon, which is the round constant. So archon here is basically another kind of operation that we're going to do, where there are a bunch of constant values, one for each of these possible rounds that we're going to go through. So this has its own constant, this has its own constant, and so on. And then what we do is to take the output of those three operations, and we do an addition operation, an XOR basically, between the first key column and the result of those three. And then that's our first column of the next round key. And then to get the next column, well, then we do an XOR of this one with the second column. So you can see that like what we're basically doing is taking that first set of like secret information and expanding it out, like kind of recursively almost, right? We're taking the output of the thing we just got and using it to generate even more new information and spread that information out till we have a whole bunch of keys. And this process will give us kind of 11 round keys in total that are like all very different, right? From just like a looking at it kind of information entropy point of view. They're going to be like, have gone through this process, which makes them look very random basically. But like on its own, this wouldn't be enough. So then like each of these operations, like the rotate word, like just literally rotates the word around. It's kind of what we saw in the shift rows, right? But just working on a column. So basically we just take the byte on the end here and we plug it onto the top, we move everything else down. That's it, super easy. Subword, literally just substitute the bytes inside the word with what we've seen in the S box. Also super easy at this point. And then finally the archon, the round constant, we add the column together with a predefined constant column. So this is the set of constant columns that we have in kind of vector form. And you can imagine, right, these are just like constituents of a block, right? And yeah, you can see they're actually quite simple here. This is literally just like, we have zeros in these. So these zeros, they do nothing, but we kind of modify these columns using this value each time. And it kind of, this is using the Galois field rules, right? The XOR rules. And it's going to kind of take that information and distort it just a little bit in an interesting way. And yeah, so this is how this works with the archon. And then, of course, we take all of those things and we end up with this thing that we do at the end of every round that we do, which is we add the round key. So we just take the block that is that round key, and the block that we've got from doing all of these operations, and we XOR them together, and we get a new block out of that. So this is just an example here. So yeah, we go through this process then. This process to just generate a whole bunch of new key columns, and we plug them back together. We get these blocks those form our round keys. And then, like, what we can do is, this is the algorithm kind of recap again. So we expand those keys, we add that very first key to the plain text block, and then we do our rounds. We substitute the bytes, we shift the rows, we mix the columns using our Galois field and our matrix multiplication, and then we add that round key, just XORing the round key that we generated in the key schedule. Do that 9 times here, right? So we've got 1 key used here, 9 rounds here, and then on that final round, we just do the same thing, but we don't mix the columns. We add the round key, and the output of all of that is an encrypted block. So that is one block that is good to go, ready, put it out the door, we've encrypted this thing. So 16 bytes, all of this stuff takes normal 16 bytes and turns it into something which you cannot get back to without the secret key. I think that's really beautiful. I think AES is like incredibly beautiful in its simplicity when you just look at this is the steps that go into it. Now, we need to talk about modes of operation. So, like, all of this just goes into the idea of, like, encrypting a single block. It doesn't tell you, like, hey, I've got a file. Like, how do I encrypt this file? For that, you kind of need to go into a mode of operation. So ECB is the first, like, mode of operation that you would just think of. Like, it's the very first thing that you would do. If I didn't tell you about modes of operation, you wanted to encrypt a file, you would just do this. Like, everyone would invent this upon having just learned that information. And that's what you do is you just take every block in your plain text, right? You divide it up into 16-byte chunks, and you run it through the algorithm. That's what ECB means. And that's fine. That can be fine. That can be totally fine. But there is a really big problem with it. And that is that it kind of leaks structural information about the plain text if you do that. It can't leak actual information from the the plain text. You can't, still without knowing the secret key, you cannot know what went into the encryption algorithm. But just take a look at these images. So this is this is an image of Tux, the Linux penguin. And you can imagine that this is just like a raw bitmap image. So this is just like, we've got 3 bytes at a time, red, green, blue. Each one of those is a byte, and it represents some color. So like, we're taking that raw bitmap data, uncompressed, and running it through ECB, the ECB mode of AES. This is what comes out if you reinterpret the output as an image. You can still see the penguin in there. Like, that is a problem. So, like, all of that data, like, we can't get back to those original colors. There's no way for us to take these colors and know, like, okay, that section was white, that section was black, that was kind of somewhere in between. We can't do that. But what we can very much know is that was an image of a penguin. So that doesn't help. That's kind of like where using these modes of operation are just as important as the algorithm itself. Like, you got to make sure that the way you use the algorithm is useful. So how can we solve this problem? And by the way, of course, like, not all data comes with this kind of like repetitive information. Like, the reason that this happens is because if I encode one white block here and one white block over here, you're going to get the same output, right? The same encoded block is going to come out because we used the same secret key, and we just took that one block and we encrypted it and we got the output. So the same thing will happen when we take this piece of white area over here and we take another one over here. We're going to get the same. That's why we get this big repeated pattern. And of course, there's some striping in there, of course, because like we have 3 colors, and then that doesn't quite add up to a nice multiple of 16, so you end up kind of cycling through those permutations of combinations of 3 colors. But yeah, you do get this big, very clear pattern. And you can even see, for instance, like when you get to these areas with gradients, like shaded areas here, they become very, very random, right? So it's really just like large repeated chunks of information. And this gets worse, by the way, if we're just talking about images here, this gets worse like the larger resolution of an image you have. Because the larger the resolution is, the more data you have to kind of represent these common areas. So you end up showing even more detail. But yeah, you can see if you kind of look at any of these gradient points, like all of this gradient around the foot basically looks totally random. How do we fix this? We use a different mode of operation called CBC. So CBC is cipher block chaining. And this is kind of a little bit less obvious. It's not the first thing you would think about. But the idea is that what we want to do is, instead of like independently encrypting each block, each 16-byte chunk of the plain text, instead we encode each of those blocks one by one, and we somehow make each next block dependent on the previous block. So in essence, what we're doing is we're kind of mixing results of previous operations in with the next operations in a reversible way. And this will solve our structural leaking problem. So this is kind of how that looks, how that works. So this is our plain text up here, each block of our plain text. You can imagine that there are many more, but in this case we've got 4 blocks. And we have something called an IV. That's the initialization vector. And this is almost like another key that we use, but this time it's not secret. So the only constraint around the IV is that you don't use the same IV more than once. So if you're going to use the same secret key to encrypt a lot of messages, you just make sure that your IV changes each time you encrypt, because you're going to send the IV along with the ciphertext. So the output is just the ciphertext, the encrypted algorithm, the encrypted output, together with this IV, and we send the IV in plain text, right? We have to know this part in order to go backwards. But knowing this part doesn't help you directly get back to this without the key. So what we do is we end up XORing the IV together with the first block of the plain text. So we add them together, GF2 to the A style, and then we plug that into AES. So we run the AES algorithm. That gives us our first block of ciphertext, and we take our next block of plain text and we XOR those two things together, and we put that into AES. Now all of this is reversible, right? If we're going to go the other way, we just take our block of ciphertext and we run it through the AES with our key, and then we XOR with the IV, and we can get back to the plain text. So this is an invertible operation. But yeah, this is kind of how it works. This is how we get to this thing. But remember, we need to vary the IV every time. And the reason you need to vary it each time is that if you use the same IV each time, over the course of many messages, someone can take your encrypted messages together with the IV, and they can extract some information about the key just from the fact that you've provided multiple samples that use the same IV. So that's where that becomes a little bit of a problem. So CBC, this mode of operation, it's a lot slower than ECB rather, because in ECB you can do everything in parallel, right? Because you're encrypting the same blocks all at the same time, same output. Whereas in CBC you have to do it one after the other, and each is dependent on the previous. So it takes a long time, but it's very secure, right? If we were to look at like a tux image from this, it would just look all completely scrambled and random. Like it would just be a completely like white noise picture on the side. So CBC is going to form the basis of how we create a MAC, right? How we kind of get our signature, to use the wrong terms. So for that, we're going to use something called CBC MAC. So obviously people have thought of this before. This isn't my invention. this is like a well-known mode of operation that you can use to generate a MAC using CBC. So what you do is you basically use CBC in the same configuration. You encrypt the plain text with the secret key in CBC, and you just take the last block that comes out, and that is your MAC. That's basically the hash, right? So in the end, we get 16 bytes out of this thing. And those 16 bytes can be used by someone else who has the secret key. They can run the same encryption, same CBC on the plain text together with the secret key, and they'll get that last block, and it should be the same. And that's how you can validate. But there are two really important points from this, that this is like an easy area where you can slip up with cryptography. Because in CBC MAC, the IV, the initialization vector, this one here, that we just said has to change every time that you run CBC with the same encryption key on your messages. When you use it as a CBC for a MAC, it can never be allowed to change. You always have to use the same value. That is because in this particular configuration, you end up leaking information if you don't do that over the course of multiple messages. Oh, sorry, that's not true. There's actually, I'll show you what happens with that in a second. It's not over the course of multiple messages. It's actually to prevent an attack that can allow you to change the first block of the plain text without having any impact on the MAC. So we'll take a look at that in a second. The second is that somehow you have to put the length of your message into the first block that you kind of run through this operation. So let's kind of take a look at that kind of in diagram form. Very similar. We don't have an IV anymore because the IV would just be all zeros, and when we XOR plain text with zeros, we get the same thing out. So we just kind of skip that step here, but you could also imagine an IV of all zeros plugging in with an XOR. And yeah, we get this, our plain text somehow has to contain the length of the total message, right? That's really important. We run that through AES, we get our text, and then we do the same chaining, and then eventually at the end here, we get out the MAC. Now, why can the initialization vector not change? Why do you have to keep it the same? Well, imagine this, right? So we're going to send out with a MAC, we're going to send out the final block. So we're sending the plain text along with this final block and the IV. Those are the things that we need to send out. When you're just encrypting a message with CBC, you send all of the ciphertext and the IV. So notice the big difference here is that when we're doing a MAC, the plain text is around, right? It's there. And in that sense, you don't really want to reveal a lot about the encrypted part because you're basically providing some kind of mapping between one and the other. Although that isn't technically insecure, it's like you still don't want to do it, right? So it is insecure. You shouldn't do that. I shouldn't speak out of turn here. Imagine this, right? An attacker can look at our first block of plain text because it's in plain text, and they flip a bit. They flip one of the bits over here, and that of course would change the output of the MAC when they go to recompute it. But we've actually got the IV over here. So what we can do is we can just flip the corresponding bit in the IV, and when we XOR those together, that change cancels out, and we end up propagating through, and we get the same MAC out on the other side. So it's kind of crazy when you think about it, but it makes sense. Because we can control both of these parts, we can actually inadvertently control the last part. So that is why we just always say that the IV has to be all zeros. It's also a little bit of a different situation, right? You're sending the plain text and the final block rather than sending the ciphertext and the IV. So you're in a different situation to begin with, but yeah, this is something to keep in mind. Because you can manipulate those things, it can really all go out of the window. Now, the reason we need the length in here is because you can do these length manipulation attacks with CBC MAC, where if we just happen to this only happens over multiple messages. So let's say we release a firmware and we've got our MAC and we didn't have the length here, that first one would be totally secure. No problem. The second time we go to issue a firmware update, well, now we need to sign again. So we're going to sign it again, and we've got all the plain text and we've got our final block out. As we start to do this, you can do a kind of analysis on this whole thing, like cryptographically, numerically. You can do some analysis and you can start to extract like information out of this. And what you can do is you can use that information you've extracted to actually modify the messages, so you can actually lengthen the message, change the length of the message, and still end up getting the same MAC out. I'm not going to go into the details now because I also find it very hard to explain. So I probably won't do it justice in any case. But that length attack is very real. So what we're going to do is we are going to just make sure that the length of the firmware that we're doing is plugged into that first plain text block. And that's pretty easy, right? Because we can just make sure that it's in our kind of metadata section, our firmware information section, and we can just make sure that we encrypt that block first, right? So nothing says that we have to do this in order. So think about the way the firmware is structured. We have the interrupt vector table, then we have our firmware information section, then we have kind of the code and everything else. And what we can do is we can just first encrypt the firmware information section, then do all of the vector table, then do all of the rest of everything else. We kind of just swap these things around, then we've got our length, and we protect against this attack. So that's kind of it. That's as far as I want to go with this explanation. It's been pretty long, and if you've managed to stick with this, well, good on you. I find this stuff really interesting. I think you probably will too. I will make sure that there are some resources in the description, and please feel free to leave a comment correcting me or asking any kind of question, and I will try my best to answer, or I will tell you that I don't know the answer. You can also join the Discord server. That's also linked below, where you can ask questions, and other people can also provide answers. And yeah, aside from that, I'm just really excited to get going on the actual implementation of this, and like bringing in the AES code and applying it to our like kind of adapting our bootloader to make use of this and to implement the CBC Mac. So I'm really excited. I hope you are too. Thanks for watching, and I'll see you next time.